Okay, so just like the other sections, I have an example for this that I want to look at and show you specifically what I really wanted to focus on for the elliptic solver this morning is the capability that we have that's called the floating boundary condition, to float boundaries between domains as you run the elliptic solver and provide a nice smooth interior when you have multiple domains. But I did want to present a couple of slides here to talk about a few things that are a little bit more general just about the solver or the solve command for structured domains and blocks. First of all, just some tips, some things that you should be aware of. A lot of times when you find that something doesn't seem to be right in your grid, even at the block level, I find that very often those issues in cells typically propagate all the way up from your connectors. So before you actually go in and spend a lot of time using our solve command to try to fix what appears to be a problem with your grid, spend a little bit of time looking at the domains and the connectors that are near those cells that appear to have issues, just to be sure that you're not wasting your time trying to run the elliptic solver, to improve something that can't be fixed with the elliptic solver, that is actually an issue with the connector possibly. Definitely be aware that the different algorithms that we have can provide or produce completely different behaviors, just like we have in these examples here on the right-hand side for two of our boundary control functions that we have for the solver. At the top is what you'll see is the default for boundary control in pointwise, the von Levante-Hilgenstock-White method, versus an older method that we've had, our method that we've had in pointwise for quite some time, Steger-Sorensen for boundary control. So Hilgenstock-White provides a very strong influence of orthogonality and spacing near these boundaries of this first grid line, whereas Steger-Sorensen also providing orthogonality and smoothness, but it doesn't as strongly enforce the spacing of this first grid line. And so what you'll see in differences between these two is possibly a little bit smoother grid with Steger-Sorensen boundary control versus better orthogonality and spacing with Hilgenstock-White, but maybe not necessarily as smooth a grid away from the boundary. So these are some of the subtle things that you kind of need to be aware of using the solve tool that we have in pointwise. Running the solver is definitely not something that's always required for all of your domains and blocks. I have had customers that I've run into that have had questions about the solve command, and I found out fairly quickly that they were smoothing every single domain and block in their grid, and that's just often very not necessary. It does obviously depend on the solver that you're using and the requirements that you have on your grid, but I've found very often that for structured grids, the algebraic TFI method that we have for domains and blocks very often is more than sufficient quality, very good quality for your solver. Something that comes up a lot in support of customers that I've seen is this next bullet here. More is definitely not equal to better. A lot of times users, especially newer to using pointwise, will take a domain or a block into the solve command and immediately start running the solver on the entity and just keep cranking and cranking and cranking on it, assuming that the longer they run it, the better the domain or the block is going to be. That's not necessarily always the case. And oftentimes is not the case. There are a lot of situations, just like this example here on the right-hand side, where you may find you want to use Hilgenstock-White and you run that domain in the solver for 5 iterations and it looks perfect. But then you run it for 5 more, up to 10 or 15, and it starts to not look so good anymore. So a lot of it is visual in terms of the results that you're getting, but definitely never assume that more is better with the solver. Sometimes it is, but oftentimes it's not. Another tool that we have in the solve command is called subgrids. It's the last tab in that panel. Subgrids allows you for structured domains and blocks to define a subset or a region within the interior of that domain or block and smooth only that portion. And it can be really, really powerful and very useful in a lot of situations, especially when you have a domain or a block that is dimensionally large, has a large number of grid points in one or more directions, because those entities will take longer to smooth the entire entity. And very often if you have an issue in a grid, it'll be very localized to a certain region, and you can create a little subgrid there and smooth only that piece, and it'll be very fast. And the nice thing about that is it won't affect any of the rest of the grid, of the domain or block that you're working on, which may be perfect already. So definitely try to make use of subgrids, and if anybody has any questions about those, we can look at that a little bit more. Okay, some more solver tips. Do not assume that the defaults are correct for your case. So this kind of goes back to the previous slide when we looked at the differences between the boundary control functions, von Levante, Hilgenstock, White, and Steger-Sorensen. We have users back in the States who love the default von Levante, and we have others that love the original boundary control Steger-Sorensen and prefer to use it all the time. It is possible for you to specify these functions in your defaults for your grid so that every time you create new domains and new blocks, they'll automatically assume these particular attributes that you prefer. And I do suggest, if you like using Steger-Sorensen all the time, set that as a default in your defaults tab so that it's always applied for you automatically. So as it says, don't assume that the defaults are going to be the best for your particular case. The other thing that's really powerful about the solve command is that you do have the ability to change spacing and angle controls, which are shown in these two frames, independently of each other, and they can be set on each individual edge of a domain. And there's exactly 4 edges in a structured domain always, and they can be set individually for each face of a structured block. So each of the 6 faces can individually be changed and set up with all of these attributes separately. So it allows you to do a lot of tailoring and fine level control over the solve command or the elliptic solver as it runs. A lot of times for situations where I do want to improve or enforce orthogonality, say for a block that's adjacent to a body or a geometry that you're working on, very often I will come in here and for the face of the block that's on the geometry, I'll leave it as von Levante, Hilgenstock, White for the boundary control, so I get that rigidly enforced orthogonality and spacing. But the rest of the faces of the block, a lot of times I come in and change the type to off or none so that it's basically not enforcing any kind of boundary control on the other faces, just the one that I'm really concerned about. Okay, boundary conditions, there's 3 that we have on their boundaries of our entity as we're running the solve command. And so if this is a domain, we're talking about the connectors around the boundaries of the domain. If it's a block, then we're talking about the domains on the boundary of the block or the block faces. The 3 options that you have for the boundary conditions are fixed. Fixed is the default in all cases. We always make the assumption that you've probably done a lot of work creating your domains or your blocks, and so we assume we're not going to change those boundaries while the solver runs. If you want those boundaries to change in the solver, you have to come in and change it here in the boundary conditions to do that. The other 2 options, floating and orthogonal. Floating is the one that we're going to kind of focus on this morning. Floating is awesome. It treats common boundaries between domains as if they were the interior of a much larger domain. So while the solver runs, those points and shape are allowed to float and move around with the solver. And then when you save the results of that, the connector between those 2 domains automatically changes its shape. The third option for boundary condition is orthogonal. This one doesn't get used quite as much, but it can be powerful in some cases. It essentially allows grid points on a boundary to move, but the shape of the boundary does not change. So the grid points can slide around in order to try to provide a more orthogonal grid at that boundary. So the example that I want to show and talk about is from the same geometry that we've been using earlier, except I've got a set of domains here on the shroud that we'll look at, including domains that resulted from an extrusion of boundary layer blocks around the blade, and then some additional topology that spans from that boundary layer block out to the periodic surfaces. And so what has been created here in terms of topology is essentially just some two-point curves or connectors from the boundary layer out to the outer boundaries of the topology. So they're all linear in shape. What we'd really like to do is have a nice smooth grid on the interior out here as we go out into these outer regions. And so that's why we're going to use the solve command on it. One of the things that it does mention here in the last bullet, the results of using the floating BC do provide permanent changes to the connector shape and distribution after you save the results from the solve command, but we do have, of course, have the ability to undo that if you're not happy with the results. So you can go back to where you were. So I'm going to pull up this example case with these domains so we can look at this. But one of the first things that I want to try to do before I actually run the solve command is to look at and adjust some of the spacing constraints in here so that they're a little bit more consistent off the top. Because if I start out with a set of domains in the solve command that already have discontinuities in spacing just due to spacing constraints that don't match, then the results that I'm going to get from the solve command aren't going to really be that much better. I'm still going to have discontinuities at those locations. So I might as well go through and try to adjust those beforehand. So just like we've done earlier, we can go through and select some spacings that we want to copy and paste those to other locations, like similar to the ones that I have highlighted in this image. Also, if you ever need to, you can use the Alt and right mouse button option endpoint-wise to find the distance between points in the GUI if you ever need to interrogate some point locations that you may not know the distance from off the top of your head. So let's switch over and read in this file and look at it. Oh, I've already read it in, so that's convenient. All right, so this is what we have to start with. And we can see these connectors away from the boundary layer region are just linear, just like in the slide. So again, the first thing I want to do is adjust some of these spacings, and then we'll go in and take the domains into the solver and look at the setup for that. All right, so let me change. My mask is already set up here, so let's zoom in some of these areas in the grid and do some copies. So I'll copy this spacing, and I'm going to paste it onto these. And likewise here. And when I'm doing this copy and paste, I don't even really have to be so concerned about what the actual values are. I just want them to match. All right. You can see on some of these smaller connectors, the actual arrow that you have to select is much smaller, of course, as well, since it's based on what's rendered is based on the arc length of the connector. All right, I'm going to adjust some of these other values as well. So we start out with something a little bit smoother. And let's see. All right, should be pretty close here. All right, so this already just changing the spacing constraints gives us a much smoother grid in general. So now I can just take these domains into the solve command, and let's switch back over here and see what we have in the slides. Oh, I was going to show Alt-right mouse button in case somebody's not seen this before. If you ever need to measure the distance between points, for instance, maybe you don't know what the spacing is here, I can come in and use the Alt key and the right mouse and select point locations. And it'll give me the distance. As I hold down the right mouse button, it'll display the distance between the 2 points in the display window, and as soon as I release, it'll actually show me in the messages down here at the bottom the location of the first point that I selected, and then the location of the second point that I selected, and in parentheses the distance between the two. One of the nice things about this is that the text in the messages window is selectable. You can select and copy this text, so if you wanted to, you could copy this spacing and paste it into an input field in the GUI somewhere else if you need to. So that's Alt-right mouse button for checking the distances between points. Questions?
Is this new to this version?
The Alt-right mouse?
Yeah.
Nope. That's been in since the beginning. Almost the beginning. Version 16. Okay. All right, so let's zoom back out. And change my mask to select these domains. And I should have changed the spacing here as well. Let's do that real quick. This is a little off. That's better. All right. Domains. And then we'll go to Grid, Solve. And over on our Edge attributes, this is the tab that we were looking at just a couple of minutes ago in the slide. So up at the top we have the boundary control function. So I've already changed it in this case and saved it set to Steger-Sorensen, which is a little more relaxed control function, a little bit smoother results, but doesn't quite enforce the spacing and orthogonality of the boundaries that Hilgenstock-White does. The other thing that we're going to specify down here is at the very bottom, boundary conditions. It's already set up for floating. You'll note when we come into this tab in the solve command that it automatically highlights or selects all of the boundaries of all of the domains that I have in the solver automatically. And I have actually specified floating and saved it for this grid to be set to all of those boundaries. You don't have to worry about the exterior of these domains or these edges that are attached to the boundary layer grids. Those are not going to float. You have to have both the domains on both sides of a connector, a common connector, in order for that connector to be floated. Okay? So since there's not another domain over here on the other side of this boundary, for instance, this particular edge will just revert to fixed boundary condition as the solver runs. And that's pretty much it, really. We can just go through after we set the BC and run the solver. So let's see what I have in the slide here. Just pointing out that I've selected Steger-Sorensen for my boundary control and floating for my BC. A couple of things to go ahead and check in our attributes tab is to see what it has set up for the surface shape for these domains. And then once we've done that, we'll go back to the Run tab, type in a number of iterations that we want to run the solver, and just start it. All right, so I'll click back over here to Attributes. And Since these domains had been created mostly or pretty much almost entirely with connectors that were database constrained, the domains themselves have been initialized automatically as parametric domains, which means, of course, that they automatically have the shape of the underlying database surface. Pointwise recognizes that as soon as we bring the domains into the solver and, of course, sets that up as the default, it also goes ahead and sets up a default database surface that it's going to use while the solver runs. So while the elliptic method is smoothing the domain and trying to improve quality and orthogonality, it's also forcing those points to lie in the parametric space of that database surface at the same time. So this all looks good. This is what I want it to be. If I came in here and I saw, for instance, that the surface shape selection, this pull down was blank, it didn't have any text on it, that would indicate to me that I had a mixed set of settings for these domains for that particular option. So that would probably mean that some of them were set up to be database constrained and some of them were not. Some of them were free. So anytime you see one of these options, one of these pull downs that's blank in this command or any of the commands, that just means that there are multiple settings for the entities that you have currently selected. I can, of course, come in here and select one of these domains individually in this tab and change its settings individually if I need to. Okay, so that all looks good. That's what we want it to use. So just like I have here in the slides, we can switch over to the Run tab, type in 50 iterations, and send it off. So 50, enter, and run. And since we're just running domains here, it runs pretty fast. It's pretty quick. So we can see immediately, just after 50 iterations, that there's a lot of change in the grid. These grid lines where these connectors are much more highly curved now than they were before. Not as much difference here because the grid pulls pretty tightly to this bottom boundary, and so it's not as flexible. It's not as easy for these points to change because of the dimension of the grid. This one's also highly curved. So if we're happy with the results from the solver, we can just click on OK and save the results, and those connectors have their shapes updated automatically to reflect the results of the solver. So these are all now mostly curved connectors resulting from the solver. These results that I have here are not necessarily the perfect results. There may be other things that I may want to do to this grid to make it better. I may have wanted to change the attributes slightly or run it for more iterations. But just as an example, this is a good case. And there's some other things that I want to look at in these domains in the examine command. So does anybody have any questions? About running the solver? Yes?
Is there a way to create a connector which is normal to another connector?
That's normal to another connector?
Yes. I mean, because normally the solution of the elliptic solver is to make the connectors normal to its source.
Well, certainly the interior grid lines, and if you're floating, it's going to try to give you orthogonality too.
Okay, so you can draw it directly?
The only way that you can specify for a connector to be normal to something is to create one that's normal to a database surface.
Okay.
Right now.
So you need a database. Okay.
Yeah, but even that's only going to be normal to the database surface. But in those cases, it'll give you, obviously, for those points local to that, it gives you perfect orthogonality. Yes?
Before you were using here this elliptic solver, you were adjusting the spacing of certain connectors, right?
Mm-hmm.
Is it possible to skip this step? Because by using here the elliptic solver, you have also possibility just to modify the spacings and the distributions of points at the connectors. Would be the result what about the results if you skip the first step?
Well, whenever you run the solver with the default settings that I used, it's essentially using the original around the boundaries of the domains, not where I'm floating, but around the boundaries. It's using the spacings from the ends of these edges and just doing an interpolation of those spacings. So if I had a spacing here and here that didn't match the domain on the other side of those connectors, it would continue to not match after I ran the solver. However, there is an option for spacing in the solver that allows you to use adjacent grid to try to match the spacing in the current domain from one that's adjacent to it. But that other domain, in this example, this boundary layer domain, would also have to be in the solver at the same time in order for adjacent grid to be used. So you can have the solver try or attempt to adjust those spacings for you while it runs at the boundary, and it'll do a really good job in most cases. The trick here is that where these connectors are located, even though I have floating, these initial spacings on these connectors are going to tend to not change very much because they're connectors while the solver runs, and that's just a quality of the solver more than anything else. So that's why I usually try to get them close to start with, even if I was going to use that adjacent grid control. Okay, so this next section is, I think, kind of like the last main section that I wanted to cover in this morning's discussion. So we've touched on a bunch of individual tools that I wanted to kind of highlight that I think come up in these types of grids. Turbine bladed type geometries, things that you run into very often, like the gaps, the fillets, using periodicity, doing extrusions to get nice boundary layer blocks and grids, and then of course also making use of our solver to further improve the quality of your grid. So one of the last things you always, of course, want to do when you're working on a grid and point-wise is to go through and look at the quality of the grid and check some diagnostics and particular functions that may be hopefully related to your solver. So just a few things here at the top. Definitely you want to always check your cell quality before you export to your solver. Hopefully there are going to be some measures that we have in pointwise that match or nearly match diagnostics that your solver requires for the quality of your grid, so that you can verify it here before you move on. Very importantly, and I remember when I first started doing meshing back when I used to work for Lockheed years and years ago in Texas, is to always make sure you check your grid again if you have to come back and make some changes. That bit me a few times pretty quickly back when I was making grids and doing the analysis too, where I would find some things need to be adjusted. I'd go in and make some adjustments to connectors and domains and not really take the time to come back and check my grid before I moved on to the solver and end up having something wrong with the grid. So always make sure that you double check your grid after you make any changes or edits. I mentioned this before when we were talking about the solve command. Almost always, very often I find that issues with cell quality inside the interior of blocks and domains is typically a result of something going on with the distribution of your connectors or possibly the shape of a connector. Sometimes that actually comes up from projection. You perform a projection of a domain and or connectors, and possibly they may end up projecting on surfaces that you didn't intend them to project on, and you end up with kinks that propagate into the interior of your domains and your blocks. So those are all kinds of things to keep an eye out for. For the specific type of grids that we're talking about right now, for structured grids, I'm sure Carolyn has other favorites that she'll talk about later, but When I'm looking at structured grids, one of the first things when I'm building a new grid and I create some new blocks is I'll always check the Jacobian analysis. And we'll look at this on one of the next slides a little bit more. Usually if I pull a block in and look at the Jacobians and they're all positive for that block, then I consider myself pretty much to be done with that block at that point, barring more changes to the grid. So I create the volume, I create the block, I check the Jacobians, they all look good. If there's nothing going on with it immediately, then I'll go on with the rest of the grid, and of course I'll come back and check it again later before the grid is actually exported. Some of the other things that I usually really like to look at are minimum included angle, and this is actual angles that are on the interior vertices of the domain cells or block cells for whatever entities that you're using the examine command for. I have built some grids for consulting projects in the past where the solver had a specific requirement just on the angle itself of all the cells. For instance, there could be no angles less than 15 degrees in any of the cells, and so that was a diagnostic that I used very often in that particular set of projects. Others that I like to look at are area, particularly area and volume ratios. Most of our solvers really don't like to have large discontinuities in your grid between cells in certain areas, especially where there's a lot of gradients. The places in your grid that you'll tend to find these things happening are places where there are junctions between domains and blocks. So connectors between domains or domains between blocks. So that's usually where you'll see those come up. So let's look at these just a little bit more. So this next slide just shows the Jacobian panel. I wanted to talk about this briefly. So when you choose a Jacobian for a structured block for the diagnostic, Pointwise goes through and calculates the Jacobians at the vertices of all the cells in the block, and it comes up and gives you this table, which is a summary of what it is calculated for that block or blocks that you're looking at. As I mentioned before, hopefully when you read it in and look at the Jacobian, all the cells will come up listed as positive, which is the case in this particular example. 300,000 cells, 100% of them are positive. For a complex geometry though, that's generally not always going to be the case. And so we have these other measures, positive skew, and negative. So if the average of the Jacobians around the vertices of the cell is positive, then it's considered to be a positive skew cell. If the average of those Jacobians is negative, it's considered to be negative skew. And if all of the Jacobians are negative for that cell, then that cell is negative, which essentially means the code considers it to be inside out. And so you need to obviously be aware of that. This is a good way to immediately highlight potential issues, especially earlier in your meshing process. You may see some issues with the shape of your topology or the layout of your topology that you can go ahead and address immediately and not have to spend time fixing things later as you create more topology in the grid. The other thing to note about this particular diagnostic is these are checkboxes, and so by default Pointwise is set up to automatically render these individual cells for you in the display window so that you can see them rendered instantly and you know hopefully where they are. There are some things that you can do to make these show up a little bit better, and we're going to talk about those situations in a few more minutes, a little bit later in this part of the presentation. So just a little bit more again about Jacobians. Obviously we want all the Jacobians to be positive for all of our cells if possible. This is just from my experience, but I have found that in a number of cases positive skew cells can be okay for a lot of solvers, particularly if the cells are what I refer to as a tent type cell, which is essentially shaped like this, where you've got two edges of the cell that are almost collinear or coplanar. I've found that a lot of solvers are okay with those types of cells. Usually if your skewing though is like a sheared cell, those tend to become more of a problem for a lot of solvers. Generally negative skews and negative cells, of course, if they're negative, most solvers are not going to like those. Anytime you read a block into the examine command for Jacobian and it shows you that all of the cells have negative Jacobian, that usually means it's left-handed. And you just need to use the edit align command to change the computational coordinates for that block. Okay. Does anybody have any questions so far on any of the things we've talked about for examine? All right. So I'm going to just go back and look at these domains that we just smoothed. And I need to work on my interface here a little bit. So this first measure that I pulled up is minimum included angle, which is the one that's on the slide. And it goes and calculates all the minimum angles for all the cells. Of course, this is at the domain level. We're not looking at volume cells. We're looking at domain cells. And so for all of the domains that I selected, it calculates the angles, every angle in every quad, and whatever the minimum angle is for that quad shows up as the minimum for that cell. And that's what I have shown here in the color bar on the left-hand side. So for all of these cells, the minimum angle is 45 degrees, which is not too bad. You may want it to be better, but all being said, it's not too bad. But the nice thing is, of course, the visual display in color over here on the right, where you can actually see where these angles are occurring, and it immediately highlights certain areas where you may want to spend a little bit more time working on the grid. So for instance, up here we have some skewing up here next to the trailing edge. We could probably pull some of these cells a little bit more down here towards the trailing edge and get rid of some of that skewing likewise over here. In some situations, some of the skewing, the minimum angles, may be a result of the topology, like this situation here where we have a junction with the connector and the boundary, and because of the shape of the connector, even though we ran the floating solver, that particular topology layout kind of limits what we can do in terms of providing orthogonality for those cells. So that would be a situation where you may want to change the topology, or you may have to add some more points in there to smooth it out a little bit more. And in this particular case, if this were a real grid, we probably would have cells clustered more to these boundaries anyway. And so the cell quality there would probably be better. So the next one I wanted to look at is just to go ahead and look at area for these cells. So we switch back over, and while we're still in examine, we can change the diagnostic. And area is up here at the top. So basically the area just kind of gives us a really good feel for the size of the cells and the distribution of those sizes. So the actual absolute value of the area is not so much of an interest to me as where the cells are distributed and how the areas are distributed. So it kind of gives you a really good feel for where your clustering is, where your coarse areas are in your grid, how quickly the grid is varying from the boundary layer out to the other regions or not. So you can kind of quickly get a good feel for where you may need more points or need to remove some points possibly. But as I mentioned, area ratio, I think, is one that's really critical for checking before you go to your solver. I'll pull down and select that from my type list. So this gives me my area ratios. Down at the bottom of my bar is essentially cells where the ratio between two cells is 1. Up at the top it gets a little bit over 2, which is not awful, but it is getting a little higher. But again, the visual feedback that you get as to where those situations are occurring immediately tells you where there may be some things in the grid that need to be worked on. Like for instance up here at this junction where this connector is with the boundary layer, the spacing across this connector in the actual boundary layer grid has a little bit of a jump in it, and so that highlights immediately. So that's actually an area that probably should have been worked on before those blocks were extruded in the first place to make that distribution a little smoother. Likewise down here we have a couple of situations across these connectors as well where there's a jump in the spacing. And so local adjustments to those spacings as well probably need to be made. So this is really good to look at both at the domain level and the block level with volume ratio before you go to your solver, because again these are the types of things, discontinuities in area and volume ratio can quickly cause a solver to be upset. All right, let's see what else we have here. Okay, and that's what I have on the next slide, just talking about volume and volume ratio, very similar to what we just looked at the 2D level for domains. Finding areas where we have pockets with large volume cells, and also possibly even more importantly, finding jumps or large discontinuities in volumes across boundaries of blocks. Okay.
Excuse me.
Yep.
Concerning your last slide, I just have a question. What is the difference between volume and component volume in the options?
The volume...
I never understood this.
Well, I don't know the exact equations, but the volume is calculated as the total volume for the cell, depending on the equation of the volume for that particular cell type. The component volume is calculated by breaking down a cell, I'm pretty sure, into tetrahedra, calculating the volumes of those tetrahedra, and then combining those up to find a component volume. Is that right, Carolyn?
Yes, component volume is most often used as a measure when you're looking at like T-Rex grids and or prism extrusions. A prism can be decomposed into three tets, 12 different ways, right? So oftentimes looking at those component volumes and seeing what the measures are of those prisms when they are broken down can be very useful when you go to your solver, because some solvers will break down the prisms.
Right. So if a prism, for instance, is sheared in one way or another, those component volumes may highlight an issue, may actually highlight that shearing, whereas just the true volume of the prism wouldn't show anything at all. Okay, so we have a handful of things left to look at here for diagnostics and examine. Using cuts, using the probe to find specific details on the interior of a grid, using the histogram is very handy for distributions of your diagnostic, and then some tricks that we use for making the display a little clearer so that you can actually see the things that you're looking for. So the first thing here that I have is just talking about using cuts for interior views of your grid. In this particular case, I went back to the boundary layer block that we extruded just a little bit earlier in this session. Usually for structured grids, you're typically going to want to look at computational coordinate planes, although you can do Cartesian cuts through structured grids just as you can for unstructured. So, and I found sometimes those can be handy, but more often than not for structured, you probably use Cartesian planes. So let's go and select our block after I change my mask. Go to examine, pick a diagnostic function, go to the cuts tab, choose a cut direction, and then to move through the cuts you can use Just adjust things here a little bit. You can use these arrows that are up here in the panel to move back and forth between cut planes. You can also just use the arrow keys on your keypad on your computer if you want to use those instead. Let's see where we are here. Yep, that always helps. Thank you. This might not really be a great example. Because this is going to be a fairly orthogonal grid. But this shows us our cut here through the interior. We can get more information about the skew that we have in the interior of the grid by looking at these cut planes. So you can scroll through those. As I mentioned, you can change the directions using these options here in the tab. Let's go back to the slide. Oh yeah, using the probe, so I can actually select cells on this cut, and they're highlighted as I mouse over them, so it's actually selecting a cell whose face is attached to the cut. And as I highlight that cell or probe it, its value is shown on the bar over here highlighted. So for this particular diagnostic, minimum included angle, the minimum angle in this particular cell is almost 74 degrees, just under 74 degrees. So you can actually get very detailed diagnostic information on the interior of your grid. I can also click on that cell and its highlighting persists. Its value stays listed on the bar, the color bar here at the right, and then I can actually probe other cells around that one or elsewhere in the grid to see how their values compare. So you can actually get two probe values there at the same time. When you don't want to see this highlighted cell anymore, you can go back to the main Examine tab and just click on this Clear Probe option to clear that out. All right, so that's the probe. I wanted to show the histogram, so that's also found in the main Examine tab. Come down here to histogram, turn it on. You can change the number of levels that are shown. But the really nice thing about the histogram is, of course, that it shows you a distribution of cells for that particular diagnostic. In this case, of course, for a minimum angle, we'd want the angles to be pretty high, close to 90 degrees. So hopefully most of our cells are up at the top of the bar, as they are in this case.
Actually, I have similar questions.
Okay.
Because there's no way that you can get the average like within the functions. You have to check every, like when you check the areas, you have to check every area to get. If I want to know the average, then
That's over here on the Extrema tab. The average value for that diagnostic, which is probably what we're seeing right here. Is that what you're asking?
yeah.
Yes.
Is there a way to, I saw there in the histogram you could export it, I guess, to some text file or something. Is it
Yes.
possible to export other stuff, other information to text file?
The histogram is the only thing we have right now that's available to export. You're talking about from the Examine command specifically? Yeah, it's just the histogram right now. But if there's something specifically that you'd like to see, let us know and we'll make a note and add that to our feature requests. Yeah, turning off the domains, this is something that I do. I think most of us do pretty consistently. So while you're in Examine, sometimes when you're looking at these scan planes, the view can become kind of cluttered. So just using Control F3 to turn off the display of all my domains, now all I see is the cut, which just gives you a much clearer view of what you're looking at for your scan plane. So that's a common switch that we use often in the office.
Does that hide them, or does it just turn them to wireframe, or what is it?
It's just
Clicking the ghost.
It's essentially just changing them, all the domains at once, to an outline display.
Okay.
But the nice thing about that is it's not affecting the individual rendering of your domains. So if you've shaded some domains, maybe I may have my blade domains shaded, for instance, and a lot of the other domains are just wireframe. You're not changing those attributes of those domains. You're just turning them all off at once. And then you can turn them all back on and they retain their attributes. That's in the view menu, by the way. I tend to use the accelerator for that a lot, but it's right here. Show domains, and then we have all these other options here for turning off the display of stuff. Okay, so sometimes we have a diagnostic we're looking at and we want to find particular cells that don't match our quality requirements for our solver. And so there's some things that you can do to find these cells. And one of the things is to use the color bar to control what's being rendered in the display window. So in this example here, if I look at my histogram, I notice that my minimum value, I've actually overridden it. And actually, I think the next slide, I think I reversed these slides. Let me see. Yep. Okay. So in this slide, I have the default max and min values for this particular diagnostic, which again is the minimum included angle. And so I have some cells down here that are in the 42.5 to 47 degrees range. There's only 3 of them according to my histogram. So these are my min and max here that are listed with the color bar in the color bar frame. These are the default values, so these are the ones that Pointwise has calculated for all of these domains that I'm looking at right now. So for all of these, this is the min and the max, and that's what it uses for the top and the bottom of the color bar. But I can override that, and that was the previous slide, by just coming in and typing in a specific value. So let's say maybe my minimum acceptable value is 45, which is going to leave 2 cells below the minimum on my histogram. The other thing that I can do is come down here and actually adjust the cells that are being rendered by default in this frame. All the cells are turned on. I can check off the in range, which means everything between the min and the max on the color bar will be turned off. And so now only those things that are above the maximum or below the min are rendered. And that's what I see here up at the leading edge or trailing edge of the case that we were looking at for the floating boundary condition. All right, so let's look at that real quick. So these are the unsolved domains. So this is going to look a good bit different, obviously, because I haven't solved it yet. But our bar here, without running the solver, we can see that our ranges go from 33 up to, again, about 89. And so if I wanted to set a specific value here to look at, I can come back over here to the color bar and expand this. Maybe I want it to be 45 or 40 or whatever we want to look at. Type in 45. There's actually quite a few cells in this case when I choose 45 for my min. So my bar updates with the histogram, so now there's 118 cells that it shows me are below the minimum value that I specified. And so if I want to see only these cells in the display, I can come over here and use the control under Show Cells to turn off those that are in range. And so now, these cells that are being rendered now in the display are those that are below my min, because those are the only cells that I have turned on to be rendered, the below and the above, and there aren't any above the max. So this is how you can go in and isolate certain cells. So if you know for one of these quality criteria that there's a certain min that's acceptable or certain max that's acceptable for your solver, then you can set that up on the color bar and have those cells pushed out beyond the min or the max and have them rendered automatically. so I can see these now more easily in the display. Again, I can turn off the display of my domain interiors if I want to make the view a little bit more clear to see those cells. And then finally, I think there's a slide that talks about using the shrink factor. So sometimes you may have cells that you're looking for that are very small in the grid and they're hard to visualize because they are so small compared to the rest of the topology. You can use this option called shrink factor that's up here close to the top under display and actually set that down to a value of 0, and what it does is it changes the rendering of all the cells that are being shown to nodes instead of cells. And nodes and pointwise always have a fixed size no matter what your zoom level is of your grid that you're working on. So if we switch this to 0 and hit enter, these cells are now all rendered as nodes. The ones up at the top too. And sometimes that actually makes it a lot easier for them to be visualized or seen in the grid. And if you have, of course, a particularly dense topology in your grid with lots of connectors, then these nodes may start interfering with the connector nodes that we have in our grid, but you can turn those off too in the view menu so that they don't interfere with what you're looking at and examine. So the nodes now that I see are only the nodes that are cells that are being rendered. So these are just kind of a few little tricks that you can play to try and visualize some cells that you're trying to find in your grid quickly. This is one that I have used quite a bit for cases where it's hard to find really small cells. The other thing that you can do to find just the minimum value, not necessarily all these cells that we have below our min, but the very min value cell is on this Extrema tab. You can tell pointwise to come over here and just zoom to minimum. And what it'll do is it'll toggle on this option to show the minimum, so it actually renders the minimum cell, which we've already got rendered in this case already, but it also will zoom up on that particular cell automatically so you can see where it is. Let me go back over here and change my shrink back to 1, so I'm looking at cells, zoom to min, and so this is our min cell. And I know that because it's outlined. And these points are actually pickable points in the display window, so I can move my rotation point to that location, and that makes it easier for me to spin my model around and look at that cell and where it is without having it rotate right out of view and lose it immediately. All right. Anybody have any questions about diagnostics? All right, I think it's just about time for us to wrap up. So I have a couple more slides here. I wanted to speak briefly about glyph, but again, I'm not going to talk too much about it because you have a short course coming up from Travis later today, which will give you a good bit more about glyph and how to use it. But just to know that you can use our scripting to really accelerate repetitive procedures or processes. You saw me use a couple of scripts, the fillet script and the squeeze con script earlier today, just as a quick example of what can be done. There are many more in our database or our exchange online that you can use, and some of these are for generating airfoil shapes automatically, actually splitting connectors where connectors intersect, which is a capability that's not in the GUI but users have requested. One of the ones that I've used a good bit in the past for consulting projects is the block diagnose. So that's a command that makes use of examine that we were just talking about, but it'll take an entire grid and look at diagnostics for the entire grid at once, give you a table of results for that diagnostic or diagnostics, and it makes it very easy and quick for you to find where you may have problems. if you have a grid that's very complex with hundreds of blocks in it, sometimes using examine, interactively like we were just doing can become a little harder, more tedious to find those issue cells. So something like this can point out to you where the issues are in your blocks, and then you can go look at those blocks individually. So there's a lot of capability available with Glyph. The second bullet in this image here just shows an example of a script that was created that will completely automate the process of generating a grid and a bladed passage like in the image that we see here. So you can go all the way from something as simple as creating these little fillet topologies that we looked at to generating an entire multi-block complex grid topology in an automated fashion. So again, you'll hear more about Glyph later today. And then finally, just the last slide, which is of course in your notebooks with some resources about some of the things that I've talked about today. We do have a tutorial, the axial turbine blade, which the geometry that we used in a few of the examples was taken from, which takes you through a whole process of meshing that particular geometry. We have videos available online. Advanced Structured Grid Techniques is one that I pulled a couple of things from for this presentation today, particularly the material about fillets, but there's a lot more in that presentation, so if you've not watched that, you should watch that video. Our script exchange that we have available, so those scripts that I used today are on this website and available for you to download. And then finally, the location, the URL for our Glyph man pages, which has everything you need to write or modify your own scripts. And that's it. Thank you. So if anybody has any questions, I'm happy to answer now, or I'm of course here all day, so I can answer any questions you have later, but I think we're almost right on time for lunch.
I have a quick question, Eric.
Uh-oh.
How often do you use the tweak command for turbine blade grids like this? Or at all?
I use the tweak command pretty frequently, actually. So the tweak command was not one that I covered here today, but it is in the edit menu. It's called tweak. It's essentially a point editor, which allows you to go in and edit individual points on the interior of a domain or block. It's a very powerful tool. I like it, and I had the request in for this feature for many years after I started at Pointwise. Of course, other users requested it too, but I found so many times when I'm working on a very complex structured grid that the issues of cells that I may have issues with in the interior are usually very isolated and sometimes very few. It's almost laughable, and I've had a friend tell me who is familiar with statistics that when I have a block that has several million cells, that it's statistically impossible for 3 or 4 of those cells to be bad. But they are. So when you use the tweak command, you can actually go in without trying to use the solve command to elliptically smooth the block. You can actually go in and hand edit a few cells' points and fix them individually without trying to run the solver. I mean, it almost doesn't make sense to use the solve command for a really large block like that when there's only a handful of cells that need to work. So that's in the edit menu, edit tweak. I definitely recommend. Thank you, Carolyn, for pointing that out.